Hello everyone, I am Sheikh Mohammad Shafiq Anwar and today I will present our work titled Pilot Free Data Detection using a coherent MAC-based Unified Network Coordinator in IoT HeadNets. This work was carried out with my co-author and supervisor Dr. Adarsh Patel. I am from School of Computing and Electrical Engineering, Indian Institute of Technology, Mandi, Himachal Pradesh, India. This presentation is organized into four parts. First, I will discuss the motivation and challenges in future IoT heterogeneous networks. Then I will introduce the proposed system model. Next, I will explain our proposed pilot free detection algorithm based on tensor decomposition. And then finally, I will present simulation results and conclude with the key findings. Now, future 6G environments will consist of thousands of IoT devices operating simultaneously. Now, these devices will belong to multiple independent networks such as healthcare systems, smart transportation, industrial IoT, environmental monitoring, drone and robotics, smart grid. To improve spectrum efficiency, this network will increasingly share the same wireless resources. While this improves utilization, it also creates severe interference challenges because they are accessed over the same resources in the same at the same time. So the main challenge in future wireless systems is no longer connectivity. Instead, it is how reliably to detect signals when thousands of devices from different networks transmit over the same resources. This dense coexistence leads to massive interference and makes conventional signal processing techniques increasingly inefficient. So to sum it up, it basically becomes more devices plus more networks plus spectrum reuse basically gives you strong massive interference. Now, in traditional wireless systems, assumes a relatively small number of users and sufficient pilot resources. In future heterogeneous networks, however, the number of devices grows drastically while pilot resources remain limited. As a result, pilots must be reused, and pilot reuse introduces pilot contamination, increasing signaling overhead, and degrades channel estimation quality. So, the more networks you deploy, the less effective pilot-based estimation of channel becomes. To address these challenges, we propose a pilot-free detection framework called Fast Alternating Least Squares for Coherent Optimal Non-Pilot Detection, which requires only a single reference bit per user. And the objective is to jointly estimate both the transmitted data and the channel from the received signal. So in the considered scenario consists of multiple independent networks transmitting simultaneously at the same time and the same frequency. And it is assumed that each of these networks schedules their user, only one of the users at the only at one coherence block, and the rest of the users remains is scheduled on other uh, on other coherence time. So so the network one basically sends their signal D1. Network one's user K1 K1's data becomes D1, which is a data vector with length R, and it gets encoded by the code S1, and the encoded data becomes D1 Kha3 S1, which is a rank on tensor. And following this, the rest of the networks encodes its own data with its code, and then sends its signal to by the shared channel for EU networks using the same frequency and time resources. And then this signal gets received at the common radio transceiver unit which is housed with L and receiving antennas. And then this combined signal is then passed on is basically passed by the network coordinator to the distributed unit of each of these constituent network. So at each DU of each constituent network, then process this signal semi-blindly to recover its data and channel using this proposed Falcon algorithm. So each of these DU basically processes each of its own network signal, and this DU can also be housed at as a edge service or cloud service as per the Open RAN architecture. To sum it up, the overall channel model becomes overall receive signal model at du becomes this y, which can be represented as a third order tensor. Now, to separate these components, we basically employ a tensor decomposition, canonical polyadic decomposition, which basically decompose a tensor into sum of rank on tensors. So here is a illustration of the third order tensor um, with with rank u. So you can write a rank u tensor as a sum of rank 1 tensors with components g1 x1 and c1 with components u x2 and cu as their components. Now this decomposition is unique under certain conditions. This condition is basically the Kruskal condition, which states that the Kruskal rank of Kruskal rank of the each sum of Kruskal rank of these each factors must be greater than is equal to twice the rank of the tensor plus 2. So this decomposition is unique up to scaling and permutation ambiguity. Now to illustrate this permutation and scaling, I have a animation here. So you can see this G1, X1, C1 combines to make these elements in red in the third order tensor, and in this green G3, X3, C3 combines to make these red elements, and if you combine these blue elements, you get G2, X2, and C2. And if you change this ordering of, if you first stack G3, X3, C3, then you stack the green components, and then you stack the blue red components, the overall tensor doesn't change, it remains unchanged. So this is called permutation ambiguity. And for scaling, if you scale and counter scale these elements g1 x1, the overall tensor remains again same. So mathematically it can be represented using equation S, where pi is the permutation matrix and lambda gx and c are the scaling matrices, which basically gives you the identity matrix if you multiply them together. So to remove the scaling ambiguity, we have assumed that since SU is known, so and we have assumed that first symbol is known, which is a reference bit. So you can scale and counter scale the x to find the data estimates. So our problem then becomes to from the received signal 4, we have to find this optimum vector HU and DU given SU. So the rest of the components basically becomes your interference term, and this can be solved using by solving this optimization problem in 5, which is to first find these matrices HS and DU with the ambiguities, with the ambiguities. So to solve this trilinear problem, we can break it into three sub-problems, three linear sub-problems, which solve 6, 7, and 8. So this 6, 7, and 8 can be solved by using this closed form expression given in 9, 10, and 11. So you update these least squares, which becomes the least squares solutions. So you update these least square solutions of H, S, and D iteratively to converge to a good solution. Now, if there is a one of the factors is constrained, then the solution becomes a orthogonal forecasted solution given in 10a. So our objective when once you find the optimum solution of H, S, H, and D, our objective is to find the find the data vector SU and DU, data vector DU and channel estimate HU given SU. So our objective is to find such a decomposition which basically decomposes the tensor into this equation 12, 13, and 14, which basically comprises the our known channel known code SU and the rest of the columns of S, and then we have to find the channel estimate of H. Followed by the rest of the components which is not known, and then the data vectors and data matrix, data vector, data estimate, followed by the rest of the unknown data columns. So to find the network index, we solve this by equation 15, which basically maximizes the alignment between the known S and the estimate of the S. So The proposed algorithm is given in here. So you can see our inputs is a receive tensor, and assume that a network's code is known to the network at the DU, and our goal is to get the data vector DU and channel vector HU. So we first update the S and G using the least squares update. Then we align the update of S and H using the equation 15 as given in the previous slide, and then we scale and counter scale the D and H to resolve the scaling ambiguity to get the final update, and you keep on doing it for a maximum number of iterations, or until this converges to a minimum. So then this DUCF and HUCF becomes my final estimates. So to evaluate the theoretical performance limits, we derive the Cramer-Rao lower bound and channel estimation error. This lower bound serves as a benchmark for assessing how close our algorithms operate to the optimal achievable performance. Here we summarize the simulation parameters. We consider multiple network configurations with varying code lengths and number of active networks. Performance is evaluated using bit error rate or normalized mean square error. We compare our methods with least squares ZF and Gini ZF baselines, where Gini ZF basically assumes the perfect knowledge of the channel. Here, number of pilots is basically L by U, where L is the data length and U is the number of network. So this figure shows BR and NMSE as a function of iterations. So we observe that rapid convergence of the Falcon algorithm. Only a small number of iterations is required to achieve a stable performance, demonstrating the efficiency of the proposed approach. So these results compare Falcon and C-Falcon against conventional baselines. So you can see the black lines represents the Gini ZF, which assumes perfect knowledge of the channel, and then followed by the purple line is the LSZF, which assumes full pilot. Here we have kept the number of pilots to be 1 to up to 8, and we have I have given the um, results of p is equal to 1 and p is equal to 8. So you can see the our method, which is in red, Falcon, uses only one reference bit and achieves the performance of the full pilot channel estimation method. And for um, with a non-orthogonal code, you can see the performance attributes after certain SNR due to the non-orthogonality nature of the data. So finally, both proposed method approves the performance of the generated benchmark while requiring no explicit pilot-based channel estimation. You can see in the right side, the NMSE performance also follows the same pattern as in the data rejection pattern. So the dark solid black line is basically the theoretical bound, and the rest of the nature is same. So to conclude, we propose Falcon and C-Falcon for pilot-free uplink detection in heterogeneous IID networks. The proposed framework supports both orthogonal and non-orthogonal coding schemes while requiring only limited reference information. We also derived theoretical performance bounds and demonstrated strong BR and NMSE performance through simulations. And as for future work, we plan to extend the framework toward fully network independent detection scenarios, basically where the number of active network users is not just one, it can be generalized to less than U. So to conclude, I thank you all for your kind attention, and I would like to acknowledge my institute, School of Computing and Electrical Engineering, IIT Mandi, and I want to thank my supervisor for his constant guidance and support, and I want to thank my lab colleagues for their supports and inputs for this work. And I will be happy to take any questions. Please don't hesitate. Thank you.